video is going to cover section 1.5, still unit 1, and this is going to be the analyzing graphs of functions. Okay, so we have a definition here at the top that the graph of a function, f, is the collection of ordered pairs x and y, or f of x, as we also know y to be equal to, such that x is in the domain of f. Okay, in other words, these values exist in that graph, and that's considered our domain between which two x values our graph lies on. Okay, a couple things we should know. Um, x and y are given by the directed distance from the opposite axis. So what that means, and I have a picture here, okay, is that the x value, let's use a different color here, the x value is the distance away from the y-axis, okay, and the y value, so this value up here, is the distance away from the x-axis. That's why it's called the directed distance. Okay, it's this many spaces away from this axis, and so forth with the x. Okay. All right, we're going to go right into an example. This one is not too long, but it's, it still has quite a bit of topics we got to cover. So let me move this a little bit, right? We have example number 1, finding the domain and range of a function. So this one should be review. We have a graph, and we're being asked to find the domain and range of f. So this is our f function right here. It starts at -1, 1. And I'm going to go ahead and label that just so we have those points. So -1, 1. That's this point right here. Okay, this point is 0, 3. This point down here is 2, -4. And then this point right here is 3, 2 or so. Yeah, it's pretty close to that. All right. So the domain of f is defined to be all of the possible x values, or interval in this case, because it's a continuous function, meaning it is connected between some point and some point. So for letter A, it looks like the domain is going to be going from left to right, okay, starting at -1. So I'm going to go ahead and start with -1, comma, and it is a solid circle, so I'm going to go ahead and include that in a bracket. And it goes all the way to this point right here at 3. So that's going to be 3. Now, 3 is an open circle, so that's going to be a parentheses. And that's pretty much it for the domain, okay? Between -1 and 3. We look for the far left and the far right, okay? I'm going to be using interval notation. If you prefer to use a different notation, such as this one, okay, the algebraic, that is perfectly fine. You decide, as long as it's correct. Letter B is asking for the range. So range is going to be going from the bottom of the graph to the top of the graph. So we can see that our lowest point here is this one, and range is the y value. So we're starting with -4. Okay, so -4. It is a solid circle or a solid piece of the line, so it's going to be another bracket, and it goes all the way to the top right here at 3, which is also a solid point. So comma 3, brackets. Okay, and finally, we have f of -1 and f of -2. So for this one, what we're going to do is I'm going to do a little bit of notation, move that a little bit. This is asking when x is equal to -1, what is y? Okay, what is f of x? So f of -1 would be the y value at -1. So I'm going to go to my x, I'm going to find -1, here it is, okay? And I'm going to go up to the graph, and it looks like my graph is at this point, and the y value is 1. So the answer for the first part is 1, okay? For the second part, we want to know when x equals -2. So at f of -2, okay, well, we're going to go to our x, and we're going to go to -2. And you can see that there actually is no point there. So -2 is out of the domain of this graph. See, it's somewhere over here. It's smaller than -1. So in this case, we can respond that it does not exist, or D and E, because there is no value at that point. Okay, and that is it for that page. Moving on. Couple notes up here at the top. You can go ahead and pause if you need to. We have that a Open or closed dots indicate that the graph does not go past that point. So like the graph we had before, we did have closed circles, closed dots on each end, which means that the graph did end on that point, okay? Um, when we don't have any points and it just has like a, it's just a line or a curve, we're going to assume that the graph goes on beyond. So that means it's going to go to infinity in most cases. Okay, just a remark for future graphs. And then we have the vertical line test, which you should know by now. We've referenced it a few times. The graph y is a function of x if and only if it passes the vertical line test. So that means that if no vertical line will cross the graph at more than 1 point. Okay, so this part should be super easy, super reviewish. Let's look at example 2 and see how this applies. It says determine if each graph represents y as a function of x. So all we have to do here is test our vertical line. For letter A, you can see right away that if I put a line through this point here, we are crossing 2 times. So this one is not a function, okay? So we can say not a function, okay? Because y is not a function of x. So you can also say like this, y is not a function of x. I just want you to be familiar with the terminology that this right here means the same as this. Y is not a function of x means it's not a function, okay? Letter B, we have, let's see, we can do a vertical line here, a vertical line here, a vertical line here, and it looks like the graph is only intersecting once on all those lines. So this one is a yes, this one is a function, and we can say that y is a function of x, okay? Last but not least, letter C, we have this weird looking graph here that has two different lines, but it's still one function, okay? So what I'm going to do here is if I put a line through here, well, obviously it only touches once. If I put it through here, it only touches once also. If I put it right through the middle, it doesn't touch anything, but that's not part of the definition. So the vertical line test, as long as it's going through the actual piece of the graph, so the graph or the curve that's going through our coordinate plane 2 times, that's when it would not qualify. So this one would be a function also for the same reason as this. Y is a function of x. Okay. So far, so good. So far, these are easy things. So let's go ahead and look at a few more examples on how to analyze our graphs. We have analyzing of graphs on how to find zeros. Okay, so we kind of did a little bit of this in the previous section where we found f of x equal to 0. A 0 by definition is an x-intercept. Okay, it's where the y value is equal to 0 and x is just some number. We also have called this in the past roots or solutions. And I went ahead and noted here, this is when f of x equals 0. The x value is when this is true. So we've already kind of done this. Okay, so I'm going to go a little bit faster here. And then we have an example. Find the zeros algebraically. I chose this one just because it has that number in the front, so we can do a little bit more practice with this kind of factoring, okay? So what we're going to do is we're going to set f of x equal to 0. So we're going to set f of x equal to 0, okay? Which means I'm going to have 0 equals all of this, 2x squared plus 13x minus 24, okay? At this point, I'm going to have to factor. So I'm going to factor here, okay? So 0 equals, and then I have my 2 parentheses, okay? And I have to figure out what goes here. I'm going to go ahead and do this kind of on the side here because I know that some of us are still having trouble with that. So I'm going to use the slide and divide method, okay? Which is where you multiply this number over here. So I'm going to go ahead and multiply 2 times negative 24, and that's going to give me negative 48. And I'm going to hold on to my 2 up here in a corner somewhere. Okay, so this 2 is up here. So now I have x squared plus 13x minus 48. Okay, and I can factor this part. This one's not too bad. Let's see, I need to find numbers that are going to multiply to negative 48, okay, and are going to add up to 13. So I know that 16 times 3 is 48, and 16 minus 3 is going to give me 13. So I can go ahead and choose that. I'm going to do 16 and 3. One of them has to be negative because I have a negative 48. That means one should be negative. Um, since my middle number is positive, though, I'm going to keep my bigger number positive. So it's going to be plus 16 minus 3, okay? And now I have to bring back that 2, so I'm going to go ahead and bring my 2 back over here and simplify. So this would be x plus 8. And this one, I have to move my 2, I have to slide them back over here. So this would be 2x minus 3, okay, equal to 0. So there are my factors. I'm going to go ahead and put them over here now. So x plus 8 and 2x minus 3. Let me focus this a bit. It looks like it's getting a little bit blurry. All right, it's the best it's going to get. All right, and then from here we just have to solve. So we have to set each of these equal to 0. X plus 8 equals 0. 2x minus 3 equals 0. And solve. So that first one is negative 8. Okay, this one we have to add 3 to both sides. So 2x equals 3, and then divide by 2. So this one, I'm going to write it here on the side because this thing is blocking it. X equals 3 halves, or 3 over 2. And these would be our zeros of the function, okay? We're going to go ahead and do a couple more because we need to practice. So let's look at letter B first. It's right here, okay? And we're going to do the same thing. We're going to set, in this case, g of x equal to 0. So I'm going to start off by setting this one equal to 0. So 0 equals square root of x minus 25. Okay, so this one's a little bit tricky because of that square root. We tend to freak out when that happens. We want to solve for x, which means we're going to have to square both sides. Okay, and that will effectively get rid of that square root. 0 squared is 0 times 0, which is just 0. So 0 equals x minus 25. Okay, we move our 25. So plus 25 plus 25. So 25 is equal to x. And we're done. So in this case, our x-intercept, or our 0, is at 25. Okay. By the way, we could extend the lesson here by graphing these. I'm going to go ahead and hold off on that simply because we do have a few more examples to do. So I don't want to take too long. Last one for this section here. H of x is equal to x squared minus 2 over x minus 1. So this was going to be a little bit tricky because we're still going to set this equal to 0. Okay, so let me start off with that. This is going to be 0. So 0 equals x squared minus 2 over x minus 1. Okay, but now to solve this, we have to be a little creative here because we have an x on the top and we have an x on the bottom. So what I'm going to do, because I see a fraction going on here, okay, I see this fraction, I'm going to put this over 1 and I'm going to cross multiply. So I'm going to cross multiply here, okay? Which means I'm going to do 0 times this guy and 1 times this guy. So it's going to look like this. 0 times x minus 1 equals, so these two equal these two. 1 times x squared minus 2. Okay, well, 0 times anything is going to give me 0. So this whole side over here is just 0. Okay, and the other side is just 1 times the same thing. So 1 times x squared is x squared. 1 times negative 2 is negative 2. Okay, and then it's just a simple solve problem at this point. So I'm going to go ahead and move my 2 over to the other side by adding 2. 0 plus 2 is 2. This is just x squared. And then just like the problem before, we're going to go ahead and square root. Oh, actually, no. opposite of what we did before. We're going to square root. But remember from a previous section that whenever you take the square root of something, you have to do the plus and minus. So in actuality, we have x is equal to plus or minus the square root of 2. And that means that this one's going to have two zeros. This one I am going to kind of do the graph real quick. It's probably going to be something like negative square root of 2 over here, and then positive square root of 2 over here. I don't know what the graph looks like, but I do know that it's going to cross on those two pieces. Okay? That's it. So this is how you find zeros of a function. You set it equal to 0, and then you got to be a little bit creative sometimes to solve for x. Okay? Moving on, we have increasing and decreasing functions. Okay, so take a moment to copy this down, this picture up here in particular, and make sure that you do try to make this line as straight as possible. It's supposed to be a horizontal line. Okay. We have that a function is increasing if the graph is going up from left to right. It's decreasing if it's going down, okay, from left to right, and it's constant if it's just kind of straight across. And that's what I kind of have here at the bottom. Okay, but before I go to the actual definitions, I just wanted to show you a visual because if people have a really hard time with this, the best way to do it is to kind of see where your arrows are going. If you were somebody walking along this path, you would be walking downwards here, you'd be walking straight across, and then you'd be going up again. So you always want to read the graph from left to right, just like if you were doing domain and range. The directions will give you the decreasing, constant, and increasing as well. Okay, so mathematically, these are the definitions. Increasing, we have that x1 is less than x2. This implies that our y at that value, so f of x1, is less than f of x2. What that means is that as we move from left to right, so from the smaller one to the bigger one, okay, the y values are going up. So this y value is smaller than this y value because, well, this one is higher up, okay? Decreasing is the opposite. So if we're going from left to right, our y values are going down. So that means that the first y value for this x is bigger than the next one because the values are getting smaller, which means that the graph is decreasing. Okay. And finally, constant we have for any x on the interval, the y's are the same because the line is just straight across. So my y's are going to be the same no matter what. Okay. Let's look at an example and see how this works. We have example number 4. Find where the functions are increasing, decreasing, or constant, and on what interval of x. So let me move up a little bit so you can see the whole thing. See if I can get this just right. There we go. All right. So we're going to go ahead and do a couple things here. We want to find where it's increasing, where it is decreasing, or constant. So it could be doing all three. It could be doing just two. It could just be doing one thing. It could be doing none of it. Or no, actually no, it has to be doing one of them at least. So let's see. What I'm going to do is I'm going to go ahead and color code what I have here first. For my increasing, I'm going to go ahead and use pink. So it looks like going from left to right, the graph is increasing here. So I have my arrows going up here. Okay. Here it's not increasing, it's going down. So whoever was walking on this hill, slid down. And then from here it starts to increase again. So my arrows are going up again here. Okay. In between, so in the middle, it looks like it is decreasing here. So those points where this is happening, they're kind of labeled for us here, are at -2. So the interval for increasing, okay, is going to be between whatever this is all the way to -2. You always want to look at the x value where it's happening. That's why it says on what interval of x. Remember that if there's no point, this is assumed to be going on forever. So that means that it's increasing from -infinity, okay, parentheses, because we can't actually reach infinity, all the way to -2. And that's the first interval. That's this interval right here, okay? So this interval is negative infinity to negative 2 on x. The second place where it's increasing is way over here. So this one starts at 2, okay, and it goes up forever. So that, I'm sorry, not up, it goes right forever. So that would be infinity there, okay. Notice that I'm not including a bracket for this because at this exact point, too, the graph is neither increasing or decreasing. It just kind of is. Okay, so we don't want to include it because it's not really doing, if you include it in one and don't include it in the other, that's not, or include it in both of them, sorry, it's not going to make sense. It's one or the other or none. So for our purposes, we're going to go ahead and just leave it as a parenthesis. Okay, so it's increasing in two places, here and here. So 2 comma infinity, okay? It is decreasing in the middle. So this one's going to be a little bit easier because it's only one spot where it's decreasing. And it looks like it's between negative 2. So again, the same spot, negative 2, all the way to here. So to 2. And it is constant nowhere. So nowhere do we see a horizontal line just going straight across. So that is it for this one. Okay, next page. We have a few more examples. So letter B, and I did not pick any points for this one, so let me just make something up here. I'm going to put negative 3 here, and I'm going to put 2 right there, and that will be my 3. Okay. All right. So in this case, it looks like the increasing is happening here. So I'm increasing here, and it's slightly increasing here, but it's still increasing nonetheless. Okay. And then it's decreasing on this point right here. So this little tiny spot right here, it's decreasing. And then it looks like this one is just a straight line. So this one would be our constant. I guess we can do it that way. So however you want to label the constant. There's really no notation for that one. So same thing. We're going to go ahead and label this piece right here. Okay, this is all pink. So this looks like it's going to be negative infinity because it's everything on the left side. Okay, all the way to this point, which is at 2. So for increasing, my interval is negative infinity, comma, 2. Okay. For decreasing, it's a small little piece. It's between this point, so 2, and this point, so 3. So between 2 and 3, it's decreasing. And last but not least, we do have a constant part of the graph here. Okay, it is constant from 3, so from this point right here, all the way to forever, so to infinity. Okay, hopefully you're kind of getting the idea now. Okay, letter C, and this one is always a tricky one for people because you see, for some reason you want to say, oh, well, this one is going down. Remember that when we are evaluating this kind of, or analyzing graphs like this, you always read from left to right. So if I'm going to take my pen and I'm going to start here, is my pen going up or down? Okay, it's going up. Remember, you have to go this way. So this one actually looks like it's increasing the entire time. Okay, so for this graph, for letter C, we would say it's increasing on the entire domain, which in this case is negative infinity to infinity. There's no decreasing, there's no constant for this one. All right, next part. We have relative minimum and relative maximum values. So let me move this up just a little bit. Go ahead and copy this down if you want to go ahead and pause here. We have, so if we can decide or decipher where graphs are increasing, decreasing, constant, we can also see that the graphs are doing this they change from one to the other at a certain point. Okay, so that point where the graph changes from negative, or I'm sorry, from increasing to decreasing or backwards, that is called a relative minimum or a maximum, depending on what's happening. Okay, So the relative minimum is when the graph the graph changes from decreasing to increasing. And you can kind of see a picture here. If the graph is doing something like this, then this is going to be a relative minimum. And it kind of makes sense. It's the lowest point on that little section of the graph. Okay. We say it's a relative minimum because there might be a part on the graph that's even lower. So that would be considered like the global minimum. This is relative because it's relative to just that tiny section. Okay. We also call this the local minimum. A relative maximum is where the graph changes from increasing to decreasing. So it's backwards. So if you have something like this one, well, then the graph goes up and then it goes down. So this is the highest point in this little part of the graph. Okay? And then it can also be called a local maximum. So we're going to do one example that has kind of all this together. Okay, and we are going to use a graphing calculator for this one because I want to show you how to find these maximums and minimums for this graph. Okay, so this function here says for the function f of x equals negative 4x squared, okay, minus 7x plus 3, we're going to find relative min or max, where it's increasing and where it's decreasing. Please take note that to find these two things, you kind of need this because if you don't know where it stops, you don't know how far it's increasing or decreasing. Okay, so I'm going to go ahead and show you again the calculator. Hopefully you can see it. I know it's always an issue with the lighting. So we're going to go ahead and plot that. So negative 4, okay, 4x squared minus 7x plus 3. And if you still haven't downloaded this, guys, for this one, you're probably going to have to because I think you do have a problem that has to do with this. Okay, so let's graph it. And there it is. Notice that we really can't see. It looks like it's a parabola, but we can't tell, so we might have to zoom out. So I'm going to go ahead and press the zoom key, and I'm going to zoom out. All right, there we go. So that looks a little bit better. Hopefully you can see that. I'm trying to move it a little bit. It looks like the maximum is going to be here. And it's a maximum, you can tell, because the graph is going up and then it's going down. So to find that maximum with this calculator, you're going to go ahead and do the trace button. Okay, actually, no, not the trace button, second trace button. We want to calculate the maximum. So that would be second trace. Okay, second is the yellow button right here. And then you're going to go ahead and click maximum, so number 4. And what you have to do is you want to kind of, it's kind of like the inspires where you have to pick a point before. So there's one side, enter, and then the other side. And you can see the little arrow kind of shows between the bounds that we're choosing. Okay, if we just select this off. There we go. So you see how it's saying, well, we want to pick it between this point. So you have to press enter one more time. And it should give it to us. There it is. It's kind of hard to see. Maybe you can see it. Remove this, but it says it's at negative 0.87 and 6.06. I'm going to write that down. So it looked like we had a maximum, okay, and that maximum was at, I'll use the same color, it's fine, at negative 0.87, comma 6.06. And we did have to use a calculator for this one because this is not an exact number, right? It's a little bit more complicated. So I'm going to sketch this just really quickly here for our reference, so we don't have to look at that really bad lighting calculator. Okay, so it looked like it was kind of something like this. Okay, with the top point here-ish. And this point right here, hopefully your graph is not as ugly as mine. This point right here, this was negative 0.87. And this up here is 6.06. Okay, so with that information, we can see that the graph is increasing all of this part. So it's going up all the way to this point right here. And that point on X is negative 0.87. Okay, and then it's decreasing on the other side. So for increasing, we can go ahead and say increasing from negative infinity all the way to this number here. So negative 0.87. okay? And it's decreasing on the other side. So negative 0.87 to infinity. Okay, and hopefully that makes sense. If you do have any issues with the calculator, let me know. You can always use Desmos. I'm pretty sure most of you are familiar with Desmos. And I think with Desmos, you can actually just click on it and it might show you what those points are. Okay, we have, I think, two more examples and then we'll be done. So these are more application problems. Here we go with average rate of change. There is a formula that goes with this one, and it looks like the following. Okay, it is f of x2 minus f of x1 divided by x of 2 minus x of 1. So if you recognize this, it's actually your y values subtracted over the x values subtracted. And it should look familiar because this is actually the slope, kind of like the slope formula. Okay, it's the change in y divided by the change in x. So here is an example of how we're going to use this formula here. It says find the average rate of change of this function, f of x is equal to x cubed minus 3x from x equals negative 2 to x equals negative 1. So in other words, they're saying between these 2 points, what is the average rate, what is the slope between those 2 points given this function? Okay, so average rate of change can be kind of considered like a slope almost. Okay, and this is a calculus concept as well. So hopefully when you get to that, you'll remember this just a little bit. So what we're going to do is we're going to use the formula and see what we need to find. We need to find these two items. We have to find these two so we can plug them in. We already have x2 and x1. They're given to us right here. So we need to find f of x2 and f of x1. Okay, so I'm going to do that right here on the bottom. So let's do f of x2 first. Well, x2 is negative 1, and I can color code this if you'd like, so we can say this is x2. Okay, so f of negative 1, okay, I'm just plugging it in. That's all I'm doing. I'm taking this value, because that's x2, and I'm plugging it into my parentheses. It's going to be equal to, I'm going to copy this now, but instead of my x's, I'm going to put parentheses. And inside those parentheses, just like we did in previous units, we're going to plug in that negative 1. This is like our function notation stuff from before. Okay, so if we evaluate this, we should be getting negative 1 to the third power is negative 1 times negative 1 times negative 1. So you have 3 negatives, so it's going to come out as a negative. Okay, in general, odd numbered negative numbers raised to an odd number exponent are going to be negative. Okay, negative times a negative is positive, so plus 3. So negative 1 plus 3 is equal to 2. So f of x2 is equal to 2. Okay, now we're going to find f of x1. And f of x1 is this guy over here. So I'm going to plug in negative 2 into this equation. Okay, so f of negative 2, okay, same thing, equals parentheses cubed minus 3 parentheses. So this I'm just getting from up here, this function here. Okay, and I'm going to plug in that negative 2 in both spots. Just like the problem, or like this part before, negative times a negative times a negative is a negative. So I just know 2 times 2 times 2, it's going to give me 8. So negative 8. Negative times a negative, positive. Positive 6. Negative 8 plus 6 is negative 2. So I have f of x2, f of x1, I have x1, and I have x2. So I'm going to go ahead and plug all these 4 numbers now into this equation. Okay, so the equation says I can rewrite it if you want, f of x2 minus f of x1 over x2 minus x1. We're using this equation here. Okay, move that up just a little bit. So plugging all this stuff in, this number is right here. So 2 minus this number is right here, -2 over x2 is up here, -1 minus, and x1 is right here, -2. And then we just simplify, okay? So -2 minus -2, that's going to turn into a positive, okay? It's going to give me a 4. This one's also going to turn into a positive, so -1 plus 2 is going to be +1. So it looks like my answer for this problem is 4, because 4 divided by 1 is 4, okay? Next one, it's the same concept, but now I'm going to go ahead and use different numbers. I'm going to go a little bit faster. So I'm going to find f of x2. I'm going to find f of x1, okay? So f of x2 in this case this is my x2, okay? So it's going to be 1 cubed minus 3 times 1. And I'm using the same exact equation over here, okay? Or I'm sorry, function over here. So that's going to be 1 cubed is 1. 1 minus 3 times 1, this is going to be 3. 1 minus 3 is -2. Okay? F of x1 is the 0. So I'm going to do 0 cubed minus 3 times 0. And 0 cubed is 0. 3 times 0 is 0. So this one is still 0. Okay? Plugging into our equation now. I'm sorry, our formula. I keep saying the wrong words here. Okay, we have x2, so that's going to be this one right here, -2 minus f of x1, so 0, x2 minus x1. So it looks like we have -2 over 1, which is just -2. So the average rate of change between these two numbers on the graph is -2. Okay, same with this side, but with the 4. And that is it for that one. We have one more problem, and I think it's a two-part problem, maybe 3 parts. Hopefully this one doesn't take too long. We've already kind of seen this before. This is even and odd functions, okay? So a while ago, we talked about symmetry, okay? About x-axis symmetry, y-axis symmetry, and origin symmetry, and this ties in directly to that, okay? So what happens is we have that a function is considered odd if for each x in the domain of f, so every x in the function, f of negative x is equal to negative f of x. And this is actually the same as origin symmetry, okay, for this one. So all we got to do is test for origin symmetry, and if it comes out, then that means that it's odd, okay? A function is even if for each x in the domain of f of negative x is equal to f of x. So every x on the right side of the graph has the same y value as the x on the left side. So this is going to be considered even, and this is the same as, not y, I'm sorry, not x, y axis symmetry. So it's a reflection over the y axis, okay? So with those definitions and with what we already know, we're going to go ahead and determine if these functions down here are odd, even, or neither. Okay, remember that for odd, this has to be true. So if I plug in negative x, this function should be equal to the negative y. Okay, for even, my negative x should be the same as the x, as the original. So here's kind of a method that I put here on the slide. I said letter A is f, this is our problem, f of x equals 5 minus 3x. So the method is to find f of negative x because both of these have that. Look, they both have that. So we have to find that for sure. And we're going to find negative f of x. Once we have those, we can compare and say, well, which one is it? Is it equal to the original? Are these two equal? What's going on? Okay, so let's go ahead and do that. And there was some questions about this. So, if you have more questions, by all means, let me know. Okay, so we're going to go ahead and plug in negative x first for this one. Okay, so it's going to look like this: 5 minus 3 times negative x, okay? And that is going to give me, let's see, 5. The two negatives here are going to be positive, so plus 3x. And that's it. We can't do anything past that, okay? So right off the bat, I can see that this is not equal to, remember, this is our original right here. This is the original, this guy, okay? So since this is not equal to this, that means that these two are not equal to each other. So therefore, it's not going to be y-axis symmetry. It's not going to be even because these two have to be equal for it to have even symmetry. So it's not going to be even. So not even, okay? For this one, we're going to find negative f of x. Now, this one's a little bit tricky because people don't really know what to do with that. Remember that f of x is the same as y. So what you can do with this one is you can put the negative in front of the entire function, like so. Because remember that f of x is equal to all of this. So if I put a negative here, I can put a negative here, and it would be the same thing. And if that doesn't work with you, you can also always divide by -1 and get this as well. But I think this is just easier. So if you kind of want to see what I'm doing, this right here, this parentheses is your f of x. Okay, and I'm just making it negative. I'm putting that negative right in front of it. All right, so then from here we distribute. So negative times a 5 is -5. Negative times a negative is positive 3x. Okay, so let's take a look at this now. For this one, this has to do with the odd symmetry, okay? Odd symmetry uses both of them. It says this guy has to equal this guy. So that means I would be comparing these two together. And if they're the same, that means that it's going to be odd. So let's see. This one is 5 plus 3x. This one is negative 5 plus 3x. They are not the same. Okay, so since they're not the same, this is not going to be odd either. Okay, if you want to make a note for yourself here, since 5 plus 3x is not equal to -5 plus 3x, okay, f of negative x is not equal to negative f of x. And that's the explanation for this part right here. So if it's not even, it's not odd, that means that it's neither. So this graph, or this function, I should say, is neither. It has no symmetry. And in fact, it doesn't. It's just a line that goes through a weird place. Okay. All right. Letter B. This is a little bit more complicated. We're going to do the same thing though. Okay. We're going to find those two items first. We're going to find f of, sorry, let me fix this a little bit. We're going to find f of negative x, and then we're going to find negative f of x. So, or in this case, g of x, I'm sorry. So we're going to find g of negative x, okay, first. And we're going to see if it matches what I have up here, because that's the first one. You always want to check the even one first. It's a little bit less complicated. It saves you the work if it is even. So this would be parentheses to the 4th power minus parentheses square minus 1. So wherever I have those x's, I'm going to put parentheses, okay? Negative x and negative x. Well, I know from before that if I do an even number of negatives, so there's 4 of them here, okay, and that's an even number, it's going to stay positive because it's like saying negative times a negative is positive, times another negative is negative, times another negative is positive. So in this case, the first one, this one right here, is going to be x to the 4th. It stays positive, okay? Minus, I'm bringing that minus over now. This part right here is negative x squared. So it's negative x times negative x, which is positive x. So I just write x squared. Now be careful because a lot of you are going to get confused here and say, well, there's a minus here, there's a minus there. So what I did is, and if you want, I can do it like this. This part right here, this x squared, is replacing this piece right here. That negative or that minus that's already there, I just kind of brought it over, okay? So this, when I evaluate it, square it, it stays positive, okay? But of course, we still have to bring the minus over. and then minus 1. So this is what g of negative x is equal to. And if we look at the original, okay, remember this guy is our original here in this problem, we can see that they are the same. So since they are the same, we can stop. So these are the same. So that means that this has even symmetry, and it is an even function. Let's circle this one because we want to talk about the functions right now. Okay. So once, if you do find that it's even, you can stop. That's why I was saying do the even first, because if it comes out even, we don't have to check the odd. Okay. All right. Last one. So you've seen neither, you've seen even. So this one's probably going to be odd. Okay. So let's see how this one works. We're going to do the same thing. We're going to find h of negative x first. Okay. And I'm going to go ahead and plug that in. So I'm going to have 2 parentheses cubed plus 3 parentheses. And inside those parentheses, I'm going to put that negative x. So negative x goes here, and negative x goes there. Okay? You got to be careful on this one because, again, we have, I'm going to move that 2, the 2, I'm just going to leave it here in the front. So there's my 2. Okay? Negative x cubed is the same. So this part right here, if you want to put a side note, okay, is negative x times negative x times negative x. So you can see that there's 3 of them, so it's going to stay negative. But usually we don't put 2 negative x, we put the negative in the front. So we're going to put the negative right here, and there's my x cubed. Okay? Right here we have 3 times negative x, so that's going to be minus 3x. So there is that function. This is h of negative x. Okay? Now I have to find the other one. I have to find this one where the negative is in front. Okay, so I'm gonna just how should I do this? I'm gonna put the negative right here. Okay, and remember that this right here is the same as the function. So when I rewrite this one, okay, I'm gonna put it all in parentheses and put my entire h of x in here. So 2x cubed plus 3x, and there's my negative in front. Okay, so again, this part you're taking the function, so I'm taking this function and I'm putting a negative in front. Okay, so from there, I can go ahead and distribute. So I have negative 2x cubed, negative times a positive, so right here is minus 3x. Okay, and that is what this is equal to. And hopefully you have already seen what just happened. These two are the same. So when these two are the same, that means these two are the same, and that is the definition of odd symmetry. So here we have that h of negative x is equal to negative h of x, okay, which means that we have an odd function. And I believe that that is it, guys. That's the last example. So if you have any questions, as always, let me know.